Welcome to the HiRSE Summer of AI for RSE. If you want to learn more on how AI is changing the way we write and work with research software, this collection of episodes is for you.
Hello and welcome. I'm Lars Hoffmann from the HiRSE Supercomputing Center. I co-lead the division for HPC in Applied Science and Engineering. And my research focuses on atmospheric science and geoscientific model development. For a long time, the idea of telling a computer what we want and having it work on this autonomously felt like science fiction. In software development, that is starting to change. Modern coding agents can work with repository context, make edits, run tests, and report back with reviewable changes. That can be very useful for research software engineering, but it also means that review, validation, and domain expertise become even more important. In this video, I'll show you what this looks like in practice. So this talk is about Agentic AI for research software engineering. It is concerned with faster engineering, stricter validation, and human scientific judgment. Let's start with the introduction, from typing commands to delegating tasks. Agentic AI is a new and exciting approach to software development. Agentic AI changes how we interact with computers in software development. So basically, you describe the goal, you provide the context, you let the agent act, and you review the result. So what used to be science fiction now feels surprisingly familiar. And basically, this is a transition from search to task delegation. So think about how to solve a software development task. In the past, we had the search-based approach. So you would went to a website like Google or Stack Overflow. There you would find the answers, examples, and code snippets. And then you would implement them, compile, debug, and test. The next step was conversational AI. So an example here is ChatGPT. You can ask questions, get explanations, and generate code suggestions. But still, you implement, compile, debug, and test. So nowadays we have agentic AI. So the example I'm using here in this talk is Codex. Here you delegate a task in a repository context. The agent will edit and test your code, and then you review and decide whether you are satisfied with the solution. So this is a transition from information retrieval to task delegation with human review. This figure is showing the workflow for coding agents. We are starting from a task, then we provide the context. So for example, we provide the access to the code repository and documentation. Then we are making a plan on how to implement a specific feature. Then the agent will create the code changes, the diff. It will compile and test it by itself. It will update the code changes to fix any bugs. Then you can also ask the agent to make a documentation of the changes. And then we move to the human review, where we might find we need to update the implementation plan. We might also find some context is missing for the agent to act properly, or we might even find the task needs to be revised. If the review is passed, we can move on to the commit or pull request. So the agent can prepare code, tests, documentation, and pull request-ready changes. The human defines the intent, constraint, validation criteria, and acceptance. Scientific judgment remains outside the automation boundary. So here I'm looking at a commercial solution, Codex with GPT. So what is Codex? It's an agentic coding assistant working in repository context. It turns task descriptions into reviewable diffs and summaries. It can edit across files, run tests, and iterate on failures. It's very useful for debugging, refactoring, setup, and documentation. It can explain unfamiliar or large legacy code bases. It also supports data analysis, research workflows, reports, and presentations. There are different ways to use it. So one way is with the command line interface. So you will work in the terminal. You can also integrate it in your IDE, like you can use the VS Code extension. You can use it from the web, so you can delegate tasks in the cloud. There is an app, a desktop interface, and it provides integrations like for GitHub or Slack. So for institutional RSE workflows, the agent quality is only one part of the story. For institutional workflows, things like deployment, governance, data protection, licensing, and access models also matters. In Helmholtz, we have BlaBlaDoor. So this provides access to multiple selectable, openly available large language models via our in-house route. Then open code can act as an open coding agent front end, which will use a BlaBlaDoor backed model. So in my tests, this approach was very promising, but quality depends strongly on the selected model, the context, and the task formulation. Okay, so now I'd like to show some examples of agentic AI for research software engineering. So basically, I'd like to show how to move on from creating code snippets to coding agents. The first example is the MP-Track web runner. So here the goal was to develop a web application for our atmospheric transport model MP-Track, which would then execute on a virtual machine in the cloud. Some key features of this tool are we wanted to be able to configure simulation parameters via the website. Then it should be able to launch the MP-Track simulations. We would be able to visualize and download the results, and it should provide user guidance and terms. So to give you some idea of the project size, this is about 300 lines of code in Python, so it's a rather small project. We have another 1,000 lines of code of HTML templates. So the task was set to develop a Python Flask app for running MP-Track simulations in a cloud environment. So this is using a ChatGPT assisted workflow. So basically, we would ask ChatGPT for code snippets for specific features. We would copy them into the project. We would adapt this manually. We would run, deploy, test, and debug the feature. Usually there would be errors, so we would paste the errors back to ChatGPT, ask for new code snippets, and so on until it's finally working. And then we would move on to implementing the next feature. So what worked really well here is, ChatGPT is really useful for learning Flask and cloud deployment patterns. And I also found it very useful for creating code ideas and getting explanations. What remained hard is that the context stayed fragmented. So you cannot keep all of the MP-Track source code and documentation in a single ChatGPT chat. Then the integration, testing, and debugging stayed with me. So overall, this error-driven copy and paste loops are quite tedious, we must say. So retrospectively, this was coding assistance, but not task delegation. The second example is the icon to VTK converter. Excuse me. So here the goal was to convert icon model output into visualization-ready files for ParaView. Some key features of this tool are we wanted to be able to export icon fields to VTK or XDMF, HDF5. The user should be able to select the times, levels, and regions of interest. We wanted to be able to coarsen the meshes, mainly for visualization purposes. We wanted to be able to add coastlines and longitude, latitude graticules. And the tool should also be capable of writing some statistical summaries of the data. So here the project size is about 2,200 lines of code in Python and another 700 lines of documentation. So the task was to build a Python converter from icon netcdf output to VTK XDMF for ParaView. So the Agentic AI workflow comprised the following points. So here we would basically specify the input and expected output behavior. We would provide a real icon data files as examples. Then we would let the agent implement most of the tool. We would run it to test generate output files. We would inspect those files in ParaView and then iterate on the requirements and edge cases. So what changed compared to the first example, that here the implementation was really mostly delegated. So I would guess maybe 95% of the code have been generated by AI. There was very rapid growth from prototype to usable tool. Our focus shifted to requirements and validation of the output. Correctness was judged by behavior and output. The review moved from code snippets to tool-level testing, and the agent worked across multiple files, not just isolated code snippets. So this was much closer to task delegation. There was really fast progress, but validation remained essential. Just to give you some idea of the timeline, so this is just a few days in March 2026 when we worked on this. So basically on the first day, we already had the prototype, we had the map projections and the command line interface design. Then on the next day, we implemented a setup script, logging, and an option for batch runs. Then on the following day, we implemented the mesh coarsening and an option for binary writing of output files to make that faster. Then on the fourth day, we implemented tests and CI. We also implemented the map overlays and the statistics option. And on the fifth day, we implemented XDMF HDF5 as a new output format and also added the option for the range filters and the shared grids. So just within 5 days from a prototype to a really useful tool. The third example is on agentic AI in existing codes. So here the goal is to use agentic AI to tackle specific issues and improvements in existing scientific codes. The task pattern is to start from an issue, a prototype, or some unfinished feature. Then we would split this into small reviewable tasks. We let the agent propose code, tests, docs, and cleanup, and we would validate against scientific intent and existing behavior. So some task patterns are shown here on the right. So for example, we wanted to review a specific function for edge cases. We wanted to add regression tests for a function. We needed Doxygen comments for another module of the code. We wanted to get explanation on a specific algorithm and its assumptions. We wanted to refactor data structures, implement new features and unit tests for that. We wanted to improve the command line interface and wanted to improve the document usage examples in MKDocs. So my takeaway for this is, so this works best with existing architectures and tests, and it really lowers the activation energy for long postponed engineering work. So it raises the productivity for well-scoped reviewable tasks. So one specific example is we added a new domain decomposition to the MP-Track model to be able to work with high-resolution metrological data. And the starting point here was a postdoc project which established the scientific idea and first implementation. Then the remaining work was engineering, so we had to ensure robustness, fix or handle edge cases, implement tests, and update the documentation. So there was AI-supported completion. We used AI to review and simplify parts of the implementation. We also used AI to refine the MPI communication logic. We improved the handling of edge cases, for example, when we have here air parcels or trajectories moving over the poles. And we restructured and extended the test cases, and we also used AI to improve the oxygen documentation. So AI helps turn a scientific prototype into more robust model infrastructure. Okay, so the next step is a demo. I'd like to show how to run a small testable codex task. So what we are going to do here is we will use codex to interactively inspect a netcdf file containing meteorological data and then turn this into a reusable Python command line tool for plotting near surface temperature data. So what Codex should produce, it should provide us with a reusable Python plotting tool. We want to have a command line interface. We want a surface temperature plot. We want to have basic PyTest smoke test, and we want to have a short usage documentation. So in things that require human review are the metadata inspected before coding? Are the correct variables selected? Are the units and coordinates handled correctly? Is the output scientifically plausible? And is the tool reusable? And are the tests meaningful? So here's the workflow for the demo. The first step would be to inspect the metadata and data. So we want to identify the variables, dimensions, units, and coordinates in the netcdf file before writing the code. The second step is to build the Python command line tool for plotting the data. So here we would expect it to use things like xarray and matplotlib. We want to expose clear command line interface options and create a PNG output file. And the third step is to add some basic RSE structure. So we want to add testing, we want to have a short documentation, and clear referencing of the dependencies and a concise test summary. Throughout the process, we would have human review, so we will inspect each step for scientific plausibility, technical correctness, reproducibility, and suitability for reuse. So let me change to my terminal. Let's see. Here we have this data directory containing the netcdf file with the meteorological data. So next I would start a codex here on the command line. And then we can already start with our first prompt. So inspect the netcdf meteor data file under data, which variables are present, which coordinates and units. I'd like to create a plot of near surface temperature. So now this would give you a number of log messages of different steps which are being conducted. So you can see it's calling different tools like ls or a ripgrep to figure out which data and files are being present. So it's using ncdump to inspect the netcdf file. Also, it's executing some Python commands to inspect the file. So it already found the 2-meter temperature. So this looks like our final response. So So the file is our netcdf file. It contains a single time slice on a global 0.75 degree grid. These are the coordinates in the file. We have a number of surface or near surface variables. We have a number of pressure level fields or 3D fields. And then it says for a near surface temperature plot, use 2 to m. Its decoded range in the file is about 205 to 313 Kelvin. And this is already saying how could we do a minimal plot. So, but we really want a script now. So create a reusable script for plotting 2 to m. It should consider proper coordinates and units. Output should be a PNG file. Yeah, let's already try that one. And you can see here it's already looking at the Python packages, xarray, matplotlib, numpy. So here's already a first version of the code, which it has been generating now. So yeah, we can see here it's using these different packages, in particular matplotlib and xarray for handling the data and for creating the plot. We have here our parser for the command line arguments. Yeah, so says the script is in place. I'm running a syntax check and generating a sample PNG from the provided netcdf file to verify the coordinate handling and unit conversion end to end. So this was passed, and this looks like the final response. So created a plot 2 to m pi. It reads the near surface air temperature, uses the data set's lat-long coordinates, wraps longitudes from 0 to 360 degrees to minus 180 to 180 degrees for a cleaner global map, converts Kelvin to Celsius, and writes a PNG. This is how we can use it. We can provide optional arguments like for the plot title. And it says it verified it with the provided file. So syntax check passed and test image written successfully in this temporary directory. And it's already making suggestions to improve it. If you want, I can also add coastlines or a fixed geographic extent, but that would likely require an extra mapping dependency such as Cartopy. Okay, we skip that for now. We just say all this script locally, just to execute it once more. It's basically executing the Python script now to write the output here in our working directory. So that's done. Let me just go back to the terminal. Yeah, basically now next to our data directory, we have this Python script here. Yeah, that's basically what we already saw before, and it has already created this 2 to m PNG file. So let's take a look. Okay, this always looks a bit different depending on how it's actually done in the present chat. So, but overall, this looks quite reasonable. So we have latitude versus longitude. We have as a color bar, we have 2 meter temperature in degrees Celsius. So something like -60 to +30 to 40 degrees Celsius. We see here the continents. We see this very high temperatures at low latitudes over Sahara. We see very cold temperatures over Antarctica, and we have a proper plot title here. So that looks quite nice and reasonable. Okay, so I go back to Codex. Yeah, the next step was to add this RSE element. So we say add README MD with basic documentation. We would say add a simple smoke test. Yeah, document the requirements. Yeah, so the repo is still minimal, so I'm documenting the script directly and adding a smoke test that exercises the CLI end-to-end against the sample .NET file. It's adding some hardening, so then I'll add the README and the requirements txt files. So one interesting thing you could see here is this automatic approval review. So while executing things, there is like a step where the AI is kind of checking whether there is any risk in executing the commands it would provide or which you have been requesting. And based on this, it's kind of trying to assess whether there's a risk from this and whether or not it should be authorized. So, for example, here for executing this mkdir command, it says this is a narrowly scoped creation of user-requested documentation and test files within the workspace with reversible local side effects only. So risk is low, authorization high. And this is actually something you can kind of configure. You can also, let's say, how to phrase it, you can, let's say, approve things manually, or you can also use this kind of mechanism to approve things to be executed. So, okay, here's our final response. Added README, Markdown, requirements TXT, and a smoke test at tests plot 2 to m smoke pi. I also hardened the script for headless execution by forcing the backend and closing the dataset after writing. So verification passed. Yeah, maybe I will also try to just run it myself on the command line. Let's see. Yeah, passed basically. Here's our README with a brief summary of what the script is doing. Yeah, so we have the documentation, we have the requirements file. Okay, so we need matplotlib, netcdm4, pytest, and xarray. So this looks all quite reasonable. Good. So the demo result is a data analysis request became a small reusable tool with tests and documentation. We created here a number of artifacts, so the Python CLI tool, the temperature plot, the PyTest smoke test, the documentation, and the requirements have been documented. So for a review of this activity, there's the review check. So do we have the correct meteorological variable? Yes. Do we have the units and coordinate axis correct? Yes. Is the plot scientifically plausible? Yes. Is the CLI reusable and code reviewable? We've tested it for a bit, but yes. Does the test actually run the tool? Yes. And is the README enough to reproduce it? So yes. So overall, I would say scientific and technical review is passed for now, and in about 10 minutes, Codex produced here a usable tool and first results. So why this worked? This was a rather small and specific request. We have the input data or the context available in the repository. We have the metadata and units inspected properly. The output was also easy to check visually. There's no large architectural design needed here. And we had the human review before use or reuse. So in the next part, we will look at the bigger picture. So we are looking at moving from individual use to AI-assisted RSE at scale. So let's start with the question why agentic AI matters for RSE. So the point here is research software is different. So it's not just software. It has these extra constraints because it is part of the scientific method. So our code embeds not only algorithms and data structures, but also the domain knowledge, conventions, and modeling assumptions. Then the correctness matters most because software results can become scientific evidence. And reproducibility means more than testing code, so the full modeling chain must be inspectable and results must be reproducible. So the key question is, can agentic AI help us build better research software faster? And my takeaway would be that agentic AI can accelerate the engineering layer, but scientific judgment remains our responsibility. And I think when you're working with these AI tools, you really need to establish a trust boundary for that. So you need to ask yourself, what can we safely delegate? So there are things with a low risk where you can delegate freely, but still need a review. So for example, creating documentation or boilerplate code or cleanup of the command line interface or code formatting or creating usage examples. Then we have things with a medium risk where you should have small diffs. You need proper tests and explicit constraints. So this category would be, for example, code refactoring, test scaffolding, bug localization, dependency updates, or getting performance hints. And there's this high-risk category, so where we should really keep scientific judgment and final responsibility human. So this is when you're looking for new model formulations, algorithmic interpretation, numerical method changes, and when you draw scientific conclusions or make publication claims. So agentic AI is useful for engineering tasks, but it's not a substitute for scientific judgment. And you might ask yourself, how good are these AI coding agents actually? So there's a nice conference paper from 2024. So a software engineering benchmark, can language models resolve real-world GitHub issues? And the idea here for the benchmark is that the people took real GitHub issues from 12 selected Python packages. And then they looked at the issues which are linked to merge pull requests. So basically they have the problems and the solutions. And then the agent receives the issue text and the repository snapshot. and is tasked to generate a patch, which is then evaluated with the project tests. So why this matters is this is really a challenging task because we are here doing tests at the repository scale coding. We are not just asking for isolated code snippets. And what they found is primarily that the context size and code retrieval matter strongly. So you need to make sure that your AI model has a proper, can handle a proper range of tokens to keep really all the important information in its working space. And another aspect is if you have a very large code base, you need to make sure that you really find the proper files and functions to work on. So currently, leading systems resolve up to about 75% of the tasks on this SWE bench verified test suite. This is also maybe a nice historical note. In the paper, the best performing model at that time, just 2 or 3 years ago, was actually Claude 2, which was then only capable of resolving 2% of the tasks. So there's an extreme progress here in this field. And another interesting question is, how does AI show up in RSE practice? And this is a paper published just earlier this year, Advancing Research Software Engineering with AI, a research framework. So here in this study, about 1,500 Zenodo-hosted software artifacts have been analyzed. So there was an automated assessment of the RSE maturity on FAIR for RS, on the usage of AI or generative AI, and on AI Ops, ML Ops indicators. So maybe for interest, the AI usage was inferred here via LLM-based classification of the most recently modified source code files in these artifacts. And as you can see here on the right-hand side, there's basically a classification along 2 axes. So we have in the horizontal, the axis between traditional software development and AI augmented software development. And in the vertical, we have the axis from unsystematic software development towards systematic software development. So this gives us this 4 quadrants, and in the lower left, we have the quadrant of exploratory coding, which is characterized by unsystematic software development and no usage of AI, which is actually here in this study the largest part. So about 50% of the software artifacts are in this quadrant. Then on the upper left, we have the RSE quadrant. So here we have really systematic software development with best engineering practices, but no usage of AI. This is about 30% of the artifacts. And in the upper right, we have the AI for RSE quadrant. So this has both systematic software development, so established RSE practices, complemented by AI augmented software development. So this is about 8.4% of the cases. And in the lower right-hand side, we have this category of vibe coding. So this is basically unsystematic software development, but it is using AI. So this is about 11% of the cases. So main messages of the paper are AI integration and engineering maturity are largely independent. So people did not really find a strong correlation between these 2 axes. They found that this category of AI for RSE is observable, but not dominant. And the message is that AI is a production amplifier, but not a quality guarantee. And there's this idea of moving on from coding agents to science agents. So here the idea is that you move on from isolated coding assistance to increasingly automated research loops. So here on the left-hand side, we see this research loop. So we would start by generating hypotheses. We would develop the research software for that. Then we would run our workflows and experiments. We would analyze and review the results. We would publish or share the results. We would refine our models and questions, and then from this we would generate new hypotheses, and the loop continues. So the idea would be to use AI agents to support all parts of this loop. And yeah, the question is, how much can this really be achieved? So I mean, things like developing research software or running workflows and experiments is something I would clearly make a check mark. Other things like analyzing and review results can certainly be supported by AI, but the question is maybe about generating the hypothesis and refining the models and questions. This is maybe something which is really more bound to humans. So I think automation is not the same as understanding. So AI can generate plausible hypotheses, code analysis, and explanations. But scientific validity depends on assumptions, context, methodology, and evidence. So automated flows can amplify productivity and errors at the same time. So the question is, how do we make AI-assisted science trustworthy? Another interesting aspect is taking or considering AI as a learning accelerator. And I think this is really a positive aspect. So AI can support training, onboarding, and self-directed learning. So it's really great for self-education. You can use it to explain unfamiliar code, compare alternative approaches, generate small examples, create exercises and test cases, explain compiler or runtime errors, and support the onboarding into large code bases. And what's especially useful for RSE is that also scientists can learn engineering patterns, students can get immediate feedback, newcomers can ask basic questions safely, large legacy codes become more approachable, and documentation gaps become less blocking. So AI can lower the entry barrier to RSE. But there's also this mentoring dilemma, and there's this uncomfortable question. So if I can solve a task faster with AI than by training a student or a new colleague, why should I still invest the time to mentor someone? And there's the problem of the short-term pressure. So AI reduces the costs of doing things yourself. Mentoring takes time and patience. And beginners need typically small tasks and reviews of their work. On the other hand, project deadlines reward immediate output. But then from this, there's the long-term risk. So fewer people learn the principles. There's weaker intuition for bugs and limitations. There's less understanding of numerical methods. Review skills may not develop, and future teams may, in the worst case, depend on tools they cannot judge anymore. So if nobody learns the hard parts, nobody can review AI-generated work. This is addressing the question on how AI affects the RSE community. And there's a quite nice blog post from the Software Sustainability Institute from their collaborations workshops in 2025. So it's entitled, "Is AI After My Job? Navigating the Future of RSE." And here they're discussing a number of community level questions like, how will AI change the daily work of RSEs? Which skills become more important? Is it reviewing, testing, architecture, or domain translation? How do we train newcomers when AI can solve many entry-level tasks? What standards do we need for AI-assisted contributions, and how do we keep human expertise visible and valued? So I think the overall message here from this post is that AI may change RSE roles, but it also raises the value of judgment, validation, and stewardship. So where does RSE fit? So AI may accelerate things like code generation, test creation, debugging, experiment orchestration, data analysis, and documentation. And then RSE becomes even more critical for obtaining a reproducible workflows, robust software architecture, validation and verification, provenance tracking, reviewable automation, and scientific accountability. So overall, AI needs to be integrated into RSE practice and not treated as a replacement for it. So this part is on responsible use, and I'd like to provide some practical rules for AI-assisted scientific coding. So these are 10 simple rules which I took from a nice new preprint on arXiv entitled 10 Simple Rules for AI-Assisted Coding in Science. And these rules are organized in 4 themes. So the first theme is preparation and understanding. And the main message of this theme is that AI cannot fill gaps in domain understanding. So without proper preparation, we risk accepting code we cannot evaluate, debug, or maintain. So the first rule is to gather domain knowledge before implementation. So you should know the data, assumptions, units, libraries, and field conventions before implementing something. The second rule is to distinguish problem framing from coding. So AI can translate a clear plan into a code, but it should not decide the scientific method. The third rule is to choose the appropriate AI interaction model. So we have all these tools. So we can use chat for exploration, IDE assistance for local editing, and agents for reviewable repository level tasks. The second theme is context engineering and interaction. So here the message is effective AI collaboration depends on clear prompts and managed context. Particularly long or messy interactions can lose track of important details. So rule number 4 is start by thinking through a potential solution. So clarify inputs, outputs, constraints, edge cases, interfaces, and what success should look like. And rule 5 is to manage the context strategically. So you should provide the relevant files, dependencies, documentation, data examples, and critical constraints explicitly. The third theme is on testing and validation. So testing becomes even more critical when AI generates implementation code, and tests should define behavior, not just confirm that code runs. So rule number 6 is to implement test-driven development with AI. So frame your tests as behavioral specifications before requesting implementation code. And rule 7 is to leverage AI for test planning and refinement. So you can simply ask AI to identify edge cases, malformed inputs, error paths, numerical issues, and test gaps. So and the fourth theme is code quality and validation. So AI-generated code still requires careful human oversight. Passing tests does not guarantee scientific appropriateness. So rule 8 is monitor progress and know when to restart. So watch the diff, stop wrong directions early, and restart when the context becomes polluted. Rule 9 is to critically review generated code. So really test independently, read the code, and check whether the solution makes sense for the domain. And rule 10 is to refine code incrementally with focused objectives. So do not simply go to the Agentic AI tool and say, improve my code, but really ask for specific improvements such as readability, error handling, modularity, or performance. So this brings me to my conclusions. AI for RSE can be useful for things like testing, debugging, refactoring, explanations, documentation, onboarding. It can also be risky if there's implicit scientific intent, weak validation, if there are very large diffs or changes, if there are algorithmic changes, if the numerical methods are affected, and when you are drawing scientific conclusions. So we need to make it responsible. So we should have small tasks, explicit constraints, inspectable context, strong tests, reviewable diffs, and the human review. Thank you for watching. The main message I hope you take away is this. Agentic AI can be very useful for engineering work, but it does not remove the need for understanding, testing, and review. For research software, that boundary is especially important because the code is part of the scientific method. If you have questions, comments, or examples from your own work, please get in touch. I'd be very happy to continue the discussion. Thanks again and have a nice day.
Thank you for watching this episode. Please check out the slides on Zenodo linked below and see you next time.